Hi guys, welcome back to the channel. Thanks for clicking on this video. This video is going to be about this concept, rocks as batteries, and how this relates to pre-earthquake signals and also how it's going to relate to megalithic constructions. Now, this is part of a series that I'm putting together. This is the last part of this mini series on Earth's natural energies. So I made a video about telluric currents, atmospheric electricity, and this video is going to be describing in detail this concept, rocks as batteries. So please check out those other videos if you haven't seen them. Now, the point of making these videos about Earth's natural energies is because I believe that ancient megalithic constructions were meant to concentrate and amplify Earth's natural energies for the promotion of biological life. Now, what Earth's natural energies are simply low amplitude electromagnetic waves. So that's all we're talking about. We're just describing the various sources of all these low energy electromagnetic waves. And it turns out that rocks are actually one source of this energy. So large stones such as these are a common occurrence with ancient megalithic constructions. And we got to ask ourselves, why were ancient people going through such great lengths to make these amazing constructions with such large stones? So first we should understand what are rocks. So rocks are actually just aggregates of minerals. So in the case of granite, for example, which is seen here on the left, and it's a common stone used in megalithic constructions, granite is an aggregate of 3 different minerals. So any stone has to be an aggregate of at least 2 minerals. So in the case of granite, we have quartz, feldspar, and biotite. So here are what these minerals look like at the bottom: quartz, feldspar, and biotite. So if you take these minerals and combine them together, you can almost see how the chunkiness and multicolored nature of granite would encompass all 3 of these minerals. Now, what is a mineral is simply just, it's a lattice structure. So it's a very regular structure of, in this case, oxygen and silicon for quartz. And these lattice structures are what make, the minerals have these almost perfectly geometric forms, these sharp, rugged edges. Before we talk about electricity in stones, I want to first go over the magnetic properties that are associated with stones. So here you'll see we have magma. All stone was molten at one point. And as it dried and cured, such as you see here, it has these magnetic domains within it that are all jumbled around and not aligned with each other. And what happens is when the stone is molten and it's cooling off, and as it's drying, these magnetic domains can all become in alignment with each other. And they become aligned with the external magnetic field. And this external magnetic field is the magnetic field of the Earth. So the stones can capture the Earth's magnetic field lines as they were millions of years ago when the stone was cooling from its molten state. So this is actually used in paleoarchaeology to study the Earth's magnetic field as it was millions of years ago, because, like I said, the Earth's magnetic field is embedded in the stones themselves. So here's a quick video of Brian Forster, who I'll link below, a really cool guy who studies a lot of the megalithic work in South America, and he also goes to Egypt, and he's showing you how this stone at Pumapunku in South America as capable of deflecting a compass needle. So this just goes to show you that these stones really do have magnetic properties associated with them. Now, the electrical properties of crystals has long been known. So quartz crystals have what's called piezoelectricity, and this video is showing that this piezoelectricity can produce light. So in a barbecue, you'll have these this barbecue lighter here where there's a little crystal, piezoelectric crystal, and you hit this hammer down on the crystal and it produces some electricity, which makes a spark, which lights your gas. So this has long been understood, but this is not the explanation for earthquake lights. So if you have never heard of earthquake lights, it's a fascinating phenomenon that's been recorded in history for a long time, since 800 AD. So this is nothing new to us, but with all the cameras now, with all the people being able to film and the large earthquakes that have recently happened in Turkey, we're getting great video footage for the first time what earthquake lights really are. And earthquake lights are scientifically accepted. So you can see earthquake lights kind of look like lightning. They're just blue. Now this is a really interesting example, and this is kind of speculative. We don't know exactly what this is, but I would say, yeah, this qualifies as a really unique occurrence of earthquake lights. So you guys, earthquake lights don't arise from piezoelectricity. There's another phenomenon that occurs in stone. So the Earth is obviously made up of a large quantity of stone. The Earth's surface are all different types of stone, and we need to understand what the properties of stone are so we can explain earthquake lights and start to understand why ancient cultures were making megalithic constructions with stones. This is a bit of an abstract concept to wrap your head around, but when you stress rocks, it causes a separation of charges within them, and this essentially is this concept of a battery, because a battery is nothing more than maintaining a separation of charges, so then you can essentially short circuit it or create a pathway for those charges to come back together and harness that energy along the way. Rocks are capable of doing this, and it's really hard to explain the exact mechanism as to how they are capable of doing this, but the way I describe it to myself is that rocks are crystal lattice, and when you put stress on the rocks, it induces a bond breakage. So here you have this double bond between two oxygens, and when you stress it, you break this bond, okay? And this releases a relatively positive hole. And this is a very strange concept, but this positive hole is capable of moving through the stone, and in effect it will carry a positive charge. So when the bond breaks, here it's depicted as this symbol. This is the symbol, like that, and that's a positive hole. So this concept of a positive hole moving through a crystal lattice is actually part of semiconductor physics. It's referred to as semiconductor doping. So here's an example of a silicone wafer that you would use for microchips and transistors and that kind of thing. The silicone is here. This is the element silicone, and it is a crystal lattice like we were just talking about, and the doping part of this is involved putting a small amount of boron here and there in wedged in with the crystal lattice. And what you have going on basically is, if we look at this drawing here now, you have that these elements are arranged in a regular structure, hence crystal lattice, and they're bonding with each other. So they're sharing electrons, and each element here has 1, 2, 3, 4 electrons around it, except for this one that says +3. It only has 3 electrons, and that's because this element over here is borrowing this electron that was removed from this atom, and what happens is it leaves behind the absence of an electron. So everyone has 4, 4, 4. This one has 3 because it has an absence of an electron, and this is what's referred to as a hole. Now, this hole is not necessarily positive, but it's a relatively, compared to all the electrons around the hole, if you take a sampling of the negative charge around any given element here in this lattice, you're going to see it has a +4 charge. This area only has a +3 charge, so relatively speaking to the crystal lattice, it's positive. Okay, because everything is relative. And the important point here is that this positive hole can move through the crystal lattice. So in fact, it says here that they have some hole movement, and so that's because, right now it's this that's sharing the electron, but this electron sharing bond will transition to another atom over here, and now the hole is moving over here. So it's a difficult concept to fully get your head around, but that is what we're talking about when we say these positive holes are moving through the stone. So this is a paper, electric currents streaming out of stressed igneous rock. And it says a step towards understanding pre-earthquake low-frequency EM emission. So what you're going to see here depicted is a granite block right here. And this granite block is held in a vise, and this is the vise, and it's going to squish one end of this rock. It's going to put it under some pressure. And what the researchers have done is they put a copper electrode on one end of the block here and then on another end of the block here. So here's another way of viewing their setup is you have a copper electrode on the end that's being compressed, and you have a copper electrode on the end that's not being compressed. So if you look at this graph, this green triangle right here, this is representing the load that they're putting on the stone. So over the course of 10 minutes, they've put this amount of load onto the stone, 60 MPa. And you can see that as they put that load on the stone produced two charges. Two currents. One current is a positive current, and it's represented up here because this is the positive part of the graph, so it's a positive current. So the upper trace represents the current that is carried by the defect electrons, i.e. by these holes. So the hole current flows from the stressed rock volume, the source, i.e. the source, through the full length of the granite slab to the unstressed portion of the rock. You can see the circuit that is measuring the upper trace is this circuit right here to ground. So what we have happening is we have a stress being put on this end of the rock, represented by S, and you have these positive holes which are flowing out of the stressed region of the rock towards the part of the rock that's not stressed. Now you see this symbol here. This symbol is representing that it's a one-way valve, so to speak. So they're saying that this dual outflow in opposite direction implies that the boundary between the stressed and unstressed rock represents an energy barrier. So this energy barrier only lets holes pass through but rejects electrons. So what's going to happen, you guys, is electrons are going to accumulate in the stressed part of the rock, and they are not able to leave the stressed part of the rock. Only the positive holes are leaving the stressed part of the rock, and they're migrating out to the unstressed portion of the rock. So this is a separation of charge that you have occurring, where you have the positive charges on the unstressed side and all the negative charges on the stressed side. Now, if you take a copper wire and you connect the unstressed side to the stressed side, that's when you're able to close this battery and drive a current. And as I just mentioned, two currents will form. It's the movement of the positive holes towards the negative holes. They're attracted to each other because opposites attract. They want to recombine. So when you look at this graph, you're just seeing two sides of the same coin, so to speak. So the lower trace is the negative electrons. So here are the negative electrons moving out of the stress region, meeting up with the positive holes. And it says here the lower trace represents the current that is carried by the electrons. It flows from the stressed rock volumes, the source, directly into the copper electrode attached to the back end of the granite slab. So right here. So you have the negative electrons meeting the positive holes. Now, of course, this is occurring at a huge scale within the Earth all the time. And what you're seeing with earthquake lights is the release, the recombining of these positive and negative charges within the rock. Now, what could close this current in nature is obviously not going to be a copper wire. It's going to be some other natural phenomenon, such as some saline water. Now, here's another look at what's happening. We have a piston. It's stressing the rock. Like I mentioned, the positive holes are going to flow out to the unstressed region, while the negative charges are going to remain stuck by this energy barrier in the stressed region. So the stressed rock volume turns into a source of charge carriers. Mechanical work is done to activate the charge carriers. The positive holes flow into the unstressed rock, creating electrical potential. So this battery circuit can be closed by running a wire from the pistons to the unstressed end of the rock. This wire allows electrons to flow out of the stressed subvolume. So how does this work at scale? It's important to understand that we have this upper crust as represented here, and this upper crust is putting a massive amount of weight on what we're going to call the lower crust region here. So this lower crust region is constantly under stress from the upper crust being on top of it. And because it's constantly under stress, as I just previously described, it's going to have the negative, well, let's actually denote this with blue. It's going to be negatively charged. So remember, the stressed region represents an energy barrier where the electrons cannot leave unless we find a way to short circuit them. Above is going to be where all the positive holes want to go because it's the unstressed area. In fact, they're going to go all the way to the very surface of the Earth's surface. So they're going to accumulate in very concentrated forms at the peak of a mountain. So down here we have an earthquake, essentially. Now there's this effect is always occurring even when you can't feel these earthquakes, but it's especially impressive when you actually have a large magnitude earthquake. You can visually see earthquake lights, for example. But so here we have a fault, and here we have a fault, and these represent earthquakes, which is ultimately just a lot of stress being put on the stone in the earth. And like I mentioned, this stress will induce these positive charges to flow out of the rock and end up at the surface of the earth. Now, as these positive charges accumulate at the surface of the earth, they're going to generate an electrical field. So that's what these lines represent, is a concentrated electrical field. And this electrical field could become very strong around sharp points, so pyramids or natural formations at the Earth's surface, such as a mountain. And what's going to happen is it's going to generate earthquake lights. So these balls of light, these spheres of plasma, are going to form because you are creating electrical fields that are able to ionize the gas, creating plasmas and balls of light that you can visually see during an earthquake. So when there's an earthquake, that's why we get these giant blue flashes of light. And I put the moon in this depiction because the moon plays a significant role in all of this, ultimately. The moon has a gravitational influence on the Earth, and that helps loosen things up. And when tension's been building, that can help, be that straw that broke the camel's back and initiate some of these processes. So this is an example. So this kid is at the top of a mountain, obviously, and what he's experiencing is a very concentrated electrical field. And this electrical field is so strong that it's able to accelerate charged particles and ionize them. And you're listening to the sound of these particles being ionized. One thing that I touched upon in one of my other videos and has always been really interesting to me are thunderclouds and lightning strikes, so atmospheric electricity. With thunder, or with lightning rather, you get an accumulation of negative charges at the bottom of a thundercloud. Okay? And it's generally proposed that the Earth's surface is negatively charged. So all this is negatively charged. But opposite charges attract. So the bottom part of a cloud, which is negative, would never attract towards a negatively charged surface, such as the Earth. But yet lightning strikes the Earth. So why does lightning strike the Earth? Well, because below the thundercloud, the Earth becomes positive. Well, I've never received any kind of explanation as to why suddenly the Earth just becomes positively charged underneath a thundercloud, allowing the lightning to connect to the Earth. And if you look closely at lightning doesn't just come down from the cloud to the Earth. It doesn't just come and go down to Earth, as that's what it looks like. But what actually happens is it comes down quite a ways, but lightning will jump out of the surface of the Earth and connect with the lightning coming down from the cloud in midair. So I've never gotten a good explanation for where these positive charges come from until now. So this is a paper from NASA with these 3 authors, and these are reputable authors, and they state that according to the prevailing view, the global electrical circuit community, the Earth's surface is negative relative to the lower edge of the ionosphere. So this is what I've always been taught, is the Earth's surface is negative. And the reason that it's commonly believed that the Earth's surface is negative is because we have worldwide lightning strikes, about 6 per second, that constantly deliver electrons to the solid Earth, thereby charging the ground negative. Now, they say that the sign of the Earth's ground is definitely positive. And they say, here's why. Now, they say exactly what I'm describing in this video. Essentially, all crustal rocks contain proxy defects, which release positive hole charge carriers as the rocks are subject to tectonic stresses. So this is what the whole video is about. Now, they say that these positive charge carriers are highly mobile, and they spread to the Earth's surface, building up positive surface charge, just as I depicted in that last diagram. And precisely because the ground is positive, are lightning strikes attracted to the ground. So that makes a great deal of sense. The Earth's ground rapidly dissipates the electrons delivered by lightning strikes in the same way as the ground dissipates electric current from technical installations. So in conclusion, guys, loading a stone with a lot of force on one side of it will cause positive holes to flow out of the stone, and these positive holes will separate from the negative charges that reside within the stressed part of the stone. And in essence, this forces the stone into becoming a battery, and this battery is what generates the electrical energy for earthquake lights and low frequency emissions that occur before earthquakes. And where we're going with all this is taking it to megalithic construction. So here we have a giant granite box. This is the Serapeum in Egypt, and this is the King's Chamber in the Great Pyramid. And what you'll notice is that these are all large granite pieces, and the way they are stacked together, they have areas where they're being squeezed on one end by the weight of this construction. And this is going to effectively create this storage of energy. And same with this this box. It's essentially, this box is a battery. Now the caveat to it is it's not static, it's dynamic. So to charge the battery, you would have to have the weight of this structure be lifted temporarily, and then it would have to fall back down and impart that pressure once again, which essentially just means the structure has to be vibrating. It has to be resonating. And I think that's exactly what's happening. And we also have this idea of power spots or energetic points on the Earth that's related to this concept here. So that's where we're heading. I hope you learned something and got something out of this video. So thanks for watching.